class, this is Mr. Arosena, and in today's lesson we're going to talk about oxidation numbers. Alright, so oxidation numbers are a number that we use in electrochemistry, and all the oxidation number is the charge that an atom possesses if the species containing the atom were made up of ions. Now, this might sound familiar because we've already been dealing in previous science classes about charge on an atom making an ion when we were talking about making compounds way back in Science 9, I think, was when we first introduced that concept. So the oxidation number is just basically the charge of an atom when it is in compound. Now, in most cases, I shouldn't say in most cases, in a lot of cases, the oxidation number is usually the same as the ion charge. I'm going to highlight this point here, usually. Not always, though, but usually. It's the same as the ion charge list on the periodic table. But keep this in mind that there are lots of exceptions, okay? And if you end up getting oxidation numbers which are a charge which is a number much different than what you're used to for that particular element, don't worry, it's okay, you can do that. So the oxidation number is just a way of, I guess, displaying what the charge of an atom is when it is in compound form, or when it is part of a compound. And again, usually it's the same as the ion charge on the periodic table, but not always. There are a few mostly true statements, though. Mostly true. And what I mean by mostly true is that basically that in the absence of any information, the following elements will always have the following, or will always have the following oxidation number. So the alkali metals family will have oxidation numbers equivalent to +1 in almost all cases. Okay. The alkaline earth metals will have oxidation numbers of +2. Okay. Oxygen will have an oxidation number of -2, although that can change depending on the compound, but usually it's -2. Halogens will have an oxidation number equal to -1, but that can also change. And hydrogen will have an oxidation number equal to +1. So these ones here, so these mostly true statements, in the absence of any information about the compound, you can take these 5 statements as being true. In some cases, though, like especially with oxygen and halogens, sometimes their oxidation number will be different from this, but you'll probably be able to figure that out based on the context of the compound and the problem in question. Okay. Right, so that's what the oxidation number is. Now, in a compound, the oxidation number of all the things in the compound, so the sum of all the oxidation numbers, must equal the overall charge of the compound. So if the compound has a positive charge, all of the oxidation numbers when you add them together has to equal whatever that positive charge is. If there's no charge, then everything has to equal 0, basically. Okay. Now, here's an example. So here's a phosphorus compound. What's the oxidation number of phosphorus in P4? Now P4 has 0 charge, and we can tell because the compound doesn't have a charge here. It's just got, there's no charge there, so we say it has a 0 charge. So all the phosphorus oxidation numbers have to add up to 0. Okay. Now the only way that this can happen is if we take the following. So we have a 0 charge this will equal all the charges of the 4 phosphoruses added together. So this means then that phosphorus, the oxidation number of phosphorus, must be 0. Okay. Now part of this is because in most elements, or most compounds, the elements of the same type have the same oxidation number. The elements of the same type have the same oxidation number. This isn't always true though. There are some compounds, especially ones involving carbon, that this statement doesn't hold true, and you'll get cases where the carbon will, each individual carbon will actually have a different oxidation number. Like here's an example. Let's pull up, let's pull some up. Okay, so an example of that would be like, let's see, so calculate oxidation number of carbon in C3H8. Okay, so here, let's put another example. So here, the overall charge equal to 0. So we have to say, okay, so if I have an overall charge of 0, then this means that my 3 carbons plus my 8 hydrogens have to equal this 0 charge. All right, barring any other information about this compound, it's safe to assume that the hydrogens all have a +1 charge. So when we do the math here, we'll get the following: my 3 carbons plus 8. So I'll bring the 8 over. Carbon. So then carbon will have a charge of, so each individual carbon will have an oxidation number of -8/3, which doesn't make much sense, because if we're talking about atomic charges, having a fractional charge really doesn't make any sense, because you can't have fractional electrons. So this really is kind of this is, I guess you can consider this an average oxidation number. Average oxidation number for the 3 carbon atoms. Okay. So in reality, it'll probably end up being that one carbon might have a charge of, say, like -2, another carbon have a charge of -3, and the last carbon have a charge of -3. So that's one possible configuration. So one carbon is -3, or sorry, 2 carbons are -3 and 1 carbon is -2. That would be one possible configuration that does satisfy this. Or maybe you might get one carbon is -4 and 1 carbon is -3 and the last carbon is -1, or something like that. So basically, as long as the average of the carbon charges is equal to this, and that's just something that happens a lot with carbon compounds. Okay, so while this fractional oxidation number doesn't make that much sense, because we're talking about atomic charges and they're always whole numbers, it can happen in some compounds where you'll get, when you do this math to find the oxidation number, you will get this fractional oxidation number, and that just means that each individual atom actually has a different oxidation number. They're not identical. Okay. All right, but this is a not a common case. Sorry, not the usual case. Usually the oxidation numbers are whole numbers, because that makes sense. If we're talking about the transfer of electrons in a chemical compound, then it makes more sense to have the oxidation numbers as whole numbers. Okay. All right, so here's another example. Let's calculate the oxidation number of phosphorus in this particular compound. Right, so here we have an overall charge of 0 again. Okay, so say 0 will then equal to the 4 hydrogens plus the 2 phosphoruses plus the 7 oxygens. So then we can say, okay, without any other information, we'll say that the hydrogen has a charge of +1. We don't know what the phosphorus has. The oxygens have a charge of -2. Carrying out the math, that's total of +4. This will be 2p. This will be -14. All right, and then that'll be all equal to 0. So we can say, okay, let's simplify things further. This, whoops. So 4 minus this minus 10. So then this, after some, I'm gonna, whoops, yeah, that's right. P will then have to be +5. Right, so the phosphorus then has a charge of, whoops, +5. Right, which is much different than the charge of phosphorus in the previous phosphorus compound, and it's also much different than the charge of phosphorus as listed in the common periodic table. That's okay though. That's okay. So in this compound, phosphorus has a charge of +5. Okay, so I'll make a note here. Notice not the same as the common ion charge. In a table, in a periodic table. And a lot of elements will exhibit this behavior, especially if you have large elements with a lot of electrons. All right. Now, with regards to trying to figure out whether something is undergoing oxidation or reduction, there is one kind of sneaky trick that will help you figure things out very quickly. Oh, before I do that, I should do an example where the overall charge is not 0. Okay. All right. Well, honestly, the process is very similar to that. So let's try another example. This time with something that does not have oxidation number. Calculate the oxidation number of carbon in the following compound. Let's say HCO3 minus. Or it's not really a compound, it's a polyatomic ion, but whatever, same thing. All right, so overall charge is -1. That's what that negative sign, I'll put a 1 there. So then you say, okay, so -1 has to equal the following. We have 1 hydrogen plus 1 carbon plus 3 oxygens. Again, without any other information, it's safe to assume that hydrogen is +1. Carbon, we don't really know. And the oxygens are at -2. Simplifying this, we get the following. This becomes 1 plus the carbon plus -6. That, and then we can simplify this. Let's see, this is -1 equals -5 plus C. So then carbon will then have an oxidation number of +4. There we go. So even though the overall charge was negative, the process basically remains the same. We just have a different number here. All right. Right, anyways, so now on to the sneaky little trick about trying to figure out about noticing whether something becomes oxidized or reduced. So this goes back to something somebody asked in class when I was having them predict what oxidation is, and somebody mentioned, does it gain oxygen? And yes, in a lot of cases, you can tell a species undergoes oxygen if it gains oxygen molecules, or oxygen atoms, I guess. Molecules or atoms. So if the ratio of oxygen to other things increases, you can say, okay, this thing has been oxidized because it has gained oxygen atoms or oxygen molecules. Okay. Then the opposite is also true. So if a species loses oxygen molecules, you can say that it has undergone a reduction. molecules or atoms. So in this case, the ratio of oxygen to other things has decreased. An example of this would be as follows. So let's say we have carbon dioxide. If this becomes something like this, if it becomes carbonate, this is an oxidation because gains oxygen and oxygen to carbon ratio increases. Now, a reduction would basically be the exact opposite. So let's take something like a sulfate ion turning into a sulfite ion, like this. This is loses an oxygen, and the oxygen to sulfur ratio decreases. Okay. So those are some examples. Now, I mentioned that it usually means that, and there are some cases where a substance will gain oxygen molecules, but the ratio doesn't actually increase. And similarly, there's some cases where a species will lose oxygen molecules, but the ratio doesn't actually decrease. Okay, so an example of this would be like, if I were to take, say, something like, I don't know, let's say carbon dioxide, and if this during a chemical reaction goes to something like this, okay, even though it's technically gained oxygens, the ratio of oxygen to carbon hasn't changed. So this gained 2 oxygens, but the oxygen to carbon ratio is still the same. So in a case like this doesn't really get oxidized because it hasn't actually changed in terms of its oxygen to carbon ratio. Okay, and then there are other cases where you get something like this. If you have a compound like, I don't know, like this, and then it turns into CO2, it has technically lost an oxygen, but the oxygen to carbon ratio increases, going from a 3:2 ratio to a 2:1 ratio. So this is actually an oxidation despite it looking like a reduction. Okay, so make sure you check the oxygen to carbon ratio before determining whether something has been oxidized or reduced. Now this does allow you to sort of figure out based on, now you know that loss of oxygen or is a reduction, or a gain of oxygen is an oxidation. It does allow you to take certain compounds, like for example here, this is ClO3, so chlorate, this is chlorate, and you can figure out, okay, what can I turn this into if I reduce it 1 oxygen at a time? So here is ClO3. If I reduce it, I can turn this into ClO2, or I can turn this into ClO, or I can turn this into just plain Cl. So these are possible reduction products, possible reduction paths. And depending on what we want to do with the chlorate ion, we can initiate certain reactions to force it into one of these reduction paths. Okay. All right. So yeah, so that's what oxidation numbers are. Now, oxidation numbers are very useful in trying to figure out whether something has been reduced or whether something has been oxidized, because if you remember from the previous lesson, a loss of electrons is oxidation, a gain of electrons is reduction. So the oxidation number will let you sort of figure out whether something has gained electrons or whether something has lost electrons. So let's take an example. Okay. So example, which is reduced. Let's take okay, so here is an example then. ClO2 plus carbon going to, now these will obviously not be balanced, but we're just illustrating a point. 2 minus plus. All right, so we're going to be interested in either the chlorine or the carbon. So here we can figure out, okay, so what's the oxidation number of chlorine in this case? Oxidation number of chlorine, and then here we'll go oxidation number of carbon. This one's easy because it's by itself, it has no charge, so this is 0. Here, let's see, the oxygens, overall charge is 0. We have 1 chlorine and 2 oxygens, so the oxidation number of chlorine will be -4. Sorry, +4. +4. So, you know, notice here, chlorine is a halogen, but it has a oxidation number of +4. Okay. Over here, we'll do the same thing. The oxidation number of chlorine and the oxidation number of carbon. Here we have a charge of -1. We have 1 chlorine. We still have 2 oxygens. So let's see. Will end up being, the chlorine will be +3 in this case. Here the carbon will be, let's see, this is -2, 1 carbon, 3 oxygens. Carbon -6 or plus -6. Carbon will have a charge of +4. Right, so the carbon is going from a 0 oxidation number to a +4 oxidation number, so that's a loss of electrons because you're becoming more positive, so that's a loss of electrons. So this one here is a loss of electrons. Here, this one, that is a gain of electrons. So the one that's getting reduced is the one that is, let's see, gaining electrons, right? Leo, the lion, says grr. So gain of electrons reduction. So this chlorine is getting reduced because it is gaining an electron. Okay. Now looking at my compounds, my chlorine doesn't actually lose an oxygen, but it's still getting reduced because it's still gaining electrons. Okay. Meanwhile, the carbon is getting oxidized, not so much because it's gaining oxygens, it's because it's losing electrons. Okay. The gain of oxygens just happens to be a side effect of losing electrons. There you go. So there's another useful application of oxidation numbers, because we can use that to figure out what things are getting reduced and what things are getting oxidized. All right. If you have any questions, you know how to contact me. Your assignment then is as follows. And good luck.